What's good, everyone, and welcome back to another video. This video is going to be on DFS and BFS. If you guys can hear the background, I'm sorry about that. Just try to ignore it. Anyway, so BFS and DFS are basically two fundamental algorithms, and they're used for traversing or searching in graphs and trees, right? And so the in a way, it's like you want to find like the optimal way to basically explore the tree or do like finding the shortest path or pathfinder, all of that. So, and it's really good for like people use it for maze solvers and just, and this is usually like the basic kind of stuff that you wanted to learn before moving on to other things. At least that's what I believe. So DFS is depth first search. BFS is breadth first search. So I'll just go through them one at a time and explain, showing examples and things like that. So the best way to explain it, I guess, is DFS in a way is you want to, when you're looking at, for example, like a tree, ignore that. When you're looking at a tree right here, you want to go as deep as you can down one path before backtracking. And then that's for DFS. Now for BFS, it's going to be, you want to explore all the nodes at one level at a time. So like I said, DFS means we pick a path. Let's say we pick this path, and then we follow it all the way down before looking at other branches, right? So once we go all the way down, then we go back up and then go look for others, and then go back up again before following down to somewhere else, like that. That's sort of the direction that DFS is following. BFS, on the other hand, is you want to explore everything, all the nodes at each level. So with level 0 here, I want to explore everything, which is just a single node, before moving on here down here to level 1. Then I'll explore here, this node, and this node before moving down to level 2, exploring this, and this. And so, that's just like the very basic for DFS and BFS. And now I'll sort of like break it down even more, starting with DFS, obviously. So for binary trees, DFS usually come in like 3 standard orders. So we have the pre-order, which is root, left, right. We have in order, which is left, root, right. And then post order, left, right, root. There we go. Okay, so they're all DFS. Only when you visit, the node changes. Okay? So it's sort of like, think the word visit as print, collect into a list, process, whatever. The 3 traversals are just 3 different moments when we decide to visit. All right, so let me do an example. Let me draw like an example tree that we're going to use to follow. And I'm not going to do a perfect one because perfect ones are very easy, always. I'm just going to do something like that. So it's going to look a little bit different, yeah. So let's do the pre-order first. So like I said, pre-order is root, left, and then right. So the rules for pre-order, I'm going to write pre, is that for each node in, you want to first visit in, then DFS the left subtree, and then afterward you want to DFS the right subtree. Boom, 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 boom. There we go. So I'll walk through with the example on this tree right here. I'm going to write the word visit because I want to track down what I'm visiting. So we start at 1. So we visit 1. Now you want to go to the left, meaning we visit 2. and we want to go to the left again, which is 4. Now, because 4 is a leaf, there's nothing more. We can backtrack to 2, and then go to the right for 5. So we basically did this, back up, and then back down here. Now we visited 5. And now 5 is a leaf again, so now we move back to 2, and then move back to 1. Now we start going to the right side. So now we basically write down 3, and then we go to the right again for 6. And that is done. That is it. So pre-order is going to visit the node before its children. So pre-order, visit the node before its children. Okay? So there's that. Now let's try to do in order. So now I'm going to write in. In order is sort of, is going to be like exactly how it's written here, kind of. So I'm just going to, so just keep in mind the DFS left subtree, right subtree, but this time I'm just going to write it out, like simple, make it very simple. So left DFS, and then visit node, or visit node, and then right DFS, subtree. I just simplified it. So for this one, this is the rule. And this time I'm going to change the visit. Erase the arrows. Okay, so to walk through, we start at 1, but don't put anything yet, right? We go to the left for 2, and then go to the left again for 4. 4 has no children. Now that 4 has no children, we visited 4. Go back to 2, and basically it's gonna visit 2. And then now go to 5, so it's gonna visit 5. Okay? Now back to 1, so that it visits 1, and then go to the right, which is 3. Now, don't forget, this is for each node, right? Once we finish this is what I did. We start at 1 and we visit 2. And after we visit 4, because we want to go to all the way down to the very depth. And then we basically plug in that we visited 4 because there's nothing left there. When we go to 2, which that once we're at node 2, that means this is complete, and that's why we have to visit node 2, and then we visit the right side, and that's why and then after once we're at node 5, there's basically nothing for left, so we're gonna visit node 5, and then there's nothing for right, so that once we're done, then we backtrack all the way back to 1. Now 1 was here previously, but now because we already completed 1 for this part, we are now going to visit node for 1. And then after we basically printed out that we visited 1, then we go to the right side for 1. So once we visited the right side for 1, then we go to 3, right? But before we plug in the node 3, we want to visit the left side of node 3, but there's nothing. So because left is null, which I can just write it out, by the way, left is null, we can skip that and then visit 3. Now we go to the right side, which is 6. And then afterward we plug in 6. So there's that. So I can redo this just in case. So we do node 1. Yeah, one more time. So we are node 1. We do the left DFS, which goes to 2. And then now 2 does the same thing, left DFS, which goes to 4. Now 4 does the same thing, left DFS, but there's nothing. So because it's a child. So we visit the node, which is 4. And then we're gonna do a right DFS, which again comes with nothing. So that's why we have 4 in here first. Now that the 4 is done, we get rid of the 4 and we look at 2. 2 has finished its job for left DFS, so we're gonna visit the node for 2. After that, then we do the right DFS for 2. That's why it becomes 4, 2, and then 5. Now, once 2 is done, we remove 2, and now we look at 1 with its left DFS complete. Then afterward, we visit the node for 1. And then once we've written down that it's visited, then you go to the right DFS. And when you look at 3, again, you want to look at the 3 left DFS for node 3. There's nothing, it's a null, so you skip it. Then you visit the node for 3 before you move on to the right DFS for 6. And then once you've reached 6, because it's a leaf, none of this left DFS doesn't matter. You visit it and then you do the right, which again doesn't matter. So that's for in. And this would be the result. So it's slightly different compared to pre, but when you follow the steps correctly, it will just you'll be able to do it. So, and then by the way, for BST, which is binary search tree, in order traversal gives you the value in sorted order. So that's why in order is a big deal for something like the BST. Okay. Now let's do the post order. Post order will be right, left, and then visit. So, left, right, and then visit. No, visit, no. There we go. So again, I'll walk you through it. We start at 1, which is right here. And then we're going to visit, and then we're going to do the left DFS, which we're going to move on to 2. And then, so again, we start at 1, and it does this left, right? Then now that we're at node 2, node 2 is going to do its left, which is 4. Now, once we're at 4, 4 is going to do the left, which isn't going to do anything. It's going to do the right, which again doesn't do anything because it's a child. It's a leaf. Sorry, it's a leaf. 4 is the child of 2, but it's a leaf. So there's no left, there's no right. You're just going to visit the node. So that's going to show 4. Then once 4 is complete, you go back to 2, which again just did its left. So left is complete. Now we want to visit right, or we want to go to the right side, which is 5. Again, 5, it is a leaf. There's no left, there's no right. You're just going to visit the node. So it's going to be 4 and then 5. And once 5 is complete, you go back. So that you go back to 2, which did its left and just did its right. Now you're going to visit the node for 2. So there's that. Afterward, you want to go back up to 1. Now 1 just finished its left, so now it's going to go to the right side, which is 3. So you have 3 here. And now 3 again is going to do its thing. Check the left DFS, which is a null, so you skip it. And then it's going to check the right, which is 6. And 6 is a leaf, so the step 1, step 2 doesn't matter. You're just going to visit the node for 6, so you plug that in. And then you go back to 3, which you visited 3, because 3 already completed left and right, so you visit that. And then you go all the way back up to 1 once 3 is complete. And then you just plug that in. So there's that. So when we look at a tree, something like this, pre-order is going to show 1, 2, 4, 5, 3, 6. In order is going to show 4, 2, 5, 1, 3, 6. And then post order is going to be 4, 5, 2, 6, 3, 1. very different for each one of them. However, it still follows the same like DFS. You want to go all the way down to the very to the deepest part before backtracking and go off to somewhere else deepest part, the other branch deepest part. You get the idea. Now, just in case, post order is you visit the node after its children. So pre is before, post is after. And usually post is very common when it comes to like deleting a tree, basically. So okay. Damn, that was actually a lot to say for DFS. Holy. Okay, let's do BFS now. So I'm gonna erase this real quick. And there we go. Now, BFS, again, means we're going to explore the tree level by level. We want to visit all nodes at distant 1 from the root. And then all nodes at distant 2, and then so on. Or level 1, level 2, and then continue on, right? So again, okay, I don't want... Let's use the same tree, actually. Use the same tree. Boom, boom, boom. 1, 2, 3, 4, 5, and 6. So BFS, the level order traversal, it's just gonna be 1, 2. So it's just gonna be 1, 2, 3, 4, 5, 6. Actually, it's sort of like a queue. It's sort of like a queue, if you think about it. So how the BFS would kind of work is I'll kind of show it actually. So you want to first create like an empty queue, right? You want to create an empty queue. And afterward, you put the root into the queue, right? So root to queue. And then while the queue is not empty, remove the node from the front of the queue. Visit it, and then add its left child to the back of the queue if exists, and then add its right child back to the back if exists. Hopefully that makes sense. I'll show the example, obviously. So let's just walk through, right? This is 1, by the way. Node 1. Okay, so first we want to start with the empty queue. And then afterward, we want to add the 1 because that's how we start. Now, we want to pop 1. So we pop it. When we pop 1, we basically just tell them, hey, we visited 1. And then push its children, which is 2 and 3. So now Q is going to have 2 and 3. Now you want to pop 2. Which basically tells you that, hey, I visited 2. And then afterward, you push its children. So push its children, which is going to be 4 and 5. So 4, 5. Now the queue is going to look something like this. 3, 4, and 5. After that, you pop 3, which tells you that, hey, I visited 3. And then you want to push its child, which is just 6. So now it's going to look something like this. And then pop 4, meaning you visited 4, but there's no children for 4, so it's fine. And then the queue looks like this. Then you pop 5, visited 5. Q is gonna just have a 6, and then you finally pop 6, meaning you visited 6. And now the queue is empty. So once it's empty, that means you're done. Then when you look at what you visited, it's just gonna be 1, 2, 3, 4, 5, 6. Just like the tree over here, which actually when you look at it, it's very simple. And it shows how like the queue controls the order. We always pull from the front and push children to the back. So it naturally gets like a level by level traversal. Oh yeah, okay, so BFS is very, very quick. If only it didn't take that long, which is very nice. Hopefully it's understandable. If not, then I suck. But it is what it is. Maybe in the future I'll make a remake of this if a lot of people watch, obviously. Okay, so now, just in case you're asking, hey, when do I use the DFS versus the BFS? And it's sort of like a good way to want to know, like, when is it a good time to use it, since you never know, someone might ask you in your interview or whatever. But so use DFS when you want to explore all possible path downward. So all possible path downward. It's good. It's important. It's you care about recursive structure or subtree. So recursive structure subtree. A lot of tree like will have like problems where it's like compute something that depends on children, like height, diameter, path sum, etc. So you're doing in order, post order, pre order specifically. By the way, the time will be big O of n to visit all nodes. And then let's see. Yeah. Is there any extra space? Probably. Oh yeah, there is extra space. So there's extra space, by the way. Extra space. Recursive DFS uses big O of, let's call it H. Call stack. By the way, H is height of the tree. In worst case scenario, which is going to be like a skewed tree, H is going to be n. So for example, worst case scenario is going to look something like this. If that's the case, then H equals n. So it'll be big O of n stack. However, usually in a balanced tree, H will be big O of log n. So that would be, these are for the extra space, basically. So there's that. I guess I'll find a different space here to write it. Now, when you use BFS, when you sort of like care about levels or like distance. So let's say like, oh, I want to find the minimum depth. Or say like, oh, I want to find the shortest path, and I want to find the shortest path. Shortest path in an unweighted graph. There we go. And then or like nodes at distant k, for example. So there's that. What are some problems that might ask you that? Okay, so problems that sort of like ask these type of things would be like level order traversal. How do I spell it? Oh, yeah, with R. Traversal. There we go. Average of each level, or something like right side view, left side view of a tree, which often is like the BFS for level by level. And now with time, it's again, time is going to be big O of n to visit all nodes. Extra spaces would be extra space. So Q can Q can hold up to O, and then you want, like, let's say W for the width of the tree nodes. So here we have the height, and here we have the width. Worst case scenario, it's that the level is very wide, right? So it's like very, very wide. Something like this, for example. Which obviously, if you look at it, it's not very wide, but I'm just giving you an example. So if you're just looking at this graph, this is a lot wider than just looking at level 0 or something. So which, by the way, if it's worst case scenario, it can be big O of N space, by the way. There we go. And again, in a balanced tree, width is still roughly big O of N, but that one is going to be at the bottom level. And it's often manageable. So let's see. If the problem talks about like levels or shortest number of steps, then think of BFS. If the problem talks about subtree or path or recursive relationship, then that's DFS. And I think that's about it. Yeah. So in the next video, I'll probably talk about BST, which, by the way, this video itself is already long enough. I could have probably broken it down into like one about DFS and then another video about BFS, but together it's easier to sort of compare it because you usually learn both of them together, and it's always good to compare them, than on a separate video. But yeah, anyway, thanks for watching. Bye.